I'm going to make a quick video of what we did in class today for those of you that missed it. Tanky says some of you were skipping because of a lit project. I know some of you were swimming, some of you were sick. Who knows? I don't know. A car is currently worth $13,000. It's depreciating at a rate of 18% every year. What's the car worth in 6 years? Well, yesterday we talked about the equation y equals a times b to the x. That's kind of a typical classic exponential function. We also talked about p times 1 plus r over n to the nt. That was our compound interest formula. I had an a over here instead of a y, but I'm going to leave it a y because I don't want to confuse this a up here with this a over here. I'm going to keep the y over there. We are trying to find what the car is worth in 6 years. We know it started at $13,000. The interest rate is 0.18 or 18%. It's being compounded once a year. That's all we know. It says yearly. If it's being compounded yearly, that's once every year. It's to the sixth. But the difference is, I guess that's really 1 times 6. The difference with this problem and the ones we did yesterday is this depreciation thing that's going on. Since the value of the car is going down, it's actually not 1 plus, it's 1 minus. If I simplify that, I get y equals 13,000 times 1 minus 0.18, and 1 minus 0.18 is 0.82 to the sixth. Something I really want to stress, and you should have learned this before, but just to make sure we're covered. If you're losing 18% of something, you're keeping 82%. Losing 18% is the same as keeping 82%. So this 1 right here represents 100%. And we're taking 18% away from that 100%, and we're left with 82%. And now this I'm just going to do in my calculator. 13,000 times 0.82 to the sixth, $3,952.08. The car lost about $9,000 of its value in 6 years. That's what cars do. They lose their value and they lose it quickly. If you buy a new car, you know you're not going to make back the money you spent on it. The car will never be worth nothing. There's never a time when this car has no value, because even in 60 years, if it's a rusty old piece of junk, it still has metal, it still has parts, you can still scrap it. There's still some value in it, which is why the graph has that asymptote. It's going to decay, 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 but never actually cross zero. Sweet. Next. An account pays 8.2% interest, compounded daily. You've had money in the account for 6 years, and you now have this much money. How much did you start with? Well, we ended with 4906.48. We don't know how much we're starting with, so I'm going to keep that a P. But I have 1 plus 0.082. Now my end value, since this is being done... Do you have a question, Miss Miller?
There's nobody in here.
Yeah, so what am I doing?
Oh, you're taking
I'm making my video. Yeah, you want to see how this works? So right now, the computer is recording everything I'm saying, and my kids are very confused who are watching this, because they don't know that you're in the window asking me these questions. And everything I do on the board, they can see. So they can't see me, but they can see the screen. It's coming through the computer. And they're going to watch the video on YouTube. So I had a lot of kids that were gone today. Some because they were swimming, and then the rumor is there's a big lit project that no one finished, so they all just skipped. That's the rumor going around. A lot of kids gone today.
And I had a couple who, juniors?
Juniors. Pretty interesting, huh?
2 of them.
2 of them? Okay.
One of them was supposed to retake a test.
Oh, man, wasn't retaking the test he was supposed to. I'm going to press pause so we can keep talking, but my kids don't have to hear all this, 'cause it's kind of getting boring. Okay, I'm back. I apologize for that very rude interruption by Miss Miller. She kind of poked her head in the window and just started saying things. She's also wearing those really thick sunglasses that make her look like a blind person. But I think she can see, so I think we're okay there. I probably shouldn't have said that. This is being compounded daily. Daily, daily, daily. Well, there's actually 365.25 days in a year. You have to worry about leap year. You have to worry about that extra day that comes every 4 years, so that extra quarter of a day every year. In investing, they tend to do this. They worry about the leap year. It's to the 365.25 times 6. Well, this piece here is what I'm going to start with. I'm going to do this first without the p. So I calculate parenthesis 1 plus 0.082 divided by 365.25, close parenthesis, to the 365.25 times 6. Take a second, does that look okay? It does. So this comes out to p times 1.63549, yada, yada, yada. You get the idea. I don't actually have to worry about all those decimals because my calculator is going to store this decimal value in it. So now I have this equation. I divide both sides by my 1.63 thing. I'll finish that off. That's 549. 549. And up here I can do 4906 divided by 1.63549. Nope, I shouldn't do that. That's silly of me. I should divide by the previous answer. If I divide by the previous answer, I got the 0.48, I guess. Okay, I cleaned that up a little bit. I apologize for how weird it is. Doing this division, 4906.48 divided by the previous answer gives me $3,000. I started with $3,000. Okay, keep going. Minimize you and minimize you. Next. What is, if 2 to the x is 8, 2 to the x is 8, what is x? Pause and answer, unpause, x is 3. If 2 to the x is 16, what is x? You can pause it and answer if you want, but x is 4. 2 to the 4th is 16, 2 to the 3rd is 8. Well, then the question really that's left is, if 2 to the x is 12, what is x? And I paused in class and I asked this, and some kids grabbed their calculators and guessed and checked. Somebody square rooted 12, or square rooted both sides. And they thought, okay, well, the square root of 12, that's 3.46. But if I do 2 to the 3.46, I'm not going to get out 12. If I do 2 to the 3.46, I get out 11, almost exactly. So it's not 3.46. The answer is we don't actually know yet what x is. There's some x, obviously, that works. It's somewhere between 3 and 4, because that gets us 16 and 8. But we don't know what it is. This is a very important question. The reason it's an important question, suppose you have $1 million, and you want to see, well, what is that? I want to end with $1 million. You want to retire and have $1 million. Let's say right now you've got 100,000. You're already got some money in the bank. We'll be generous and give you like an 8.5% interest rate. We'll compound it monthly. Well, the question is, how long will that take? How many years will it take you to have $1 million? How long do you have to save for? That is an important question. That is a question that you're going to want to answer someday. But we can't answer it because this variable up here is in a power. And when the variable is a power, we don't really know how to solve it. If we can't answer this question, there's no way we can answer this question. And we don't want to do it by guess and check. We need a new tool. That new tool is called logarithms. It's our new section today. A logarithm is a tool we use to solve exponential equations. Logs, there's two things you hear me say over and over. Logs are exponents, and logs are inverses of exponents. Over and over and over, I'll say these things. And this is the one we're going to see the most today, but we will end kind of seeing how this happens. Before we really talk about what a log is, I'm going to show you how to work with it. So before you really know what this means, we're just going to play with it a little bit. If 3 to the second is 9, that's the exponential form. The logarithmic form is log base 3 of 9 is 2. I'm going to put these in parentheses. Your book doesn't, but I do. If 2 to the 5th is 32, log base 2 of 32 is 5. So when I say that logs are exponents, up here, logs are exponents, I'm being literal. I mean here, the exponent was 5. And this whole entire log, this whole log, is the exponent 5. The equal sign means is, and the exponent was 5. The exponent was 2, the log is 2. The log becomes the exponent. The log becomes equal to the exponent. So we'll do a couple more and then we'll go the other direction. 5 to the 3rd is 125. Well, this 5, that number there, it's called the base. It's the base of that exponent. And I call this log base 5. That number down there is read as a base. Log base 5 of 125 is 3. The base here becomes the base here. That doesn't change. The exponent here is what the log is. The log is the exponent. So that other number 125 just goes in that parenthesis. I'll put one on the screen. You should pause the screen and try it on your own. I'm done orange yet. So the log form would be and we can do this with x's as well. I could have done, well, I'll go the other way. If I have log base 2 of 16 equals 4. That right now is in the logarithmic form, log form. If I transfer that into exponential form, I do what I call the circle thing. 2 to the 4th is 16. Base to exponent to what it equals. So if I have log base 5 of 17 equals x, I do my circle thing, 5 to the x is 17. Now I don't know what x is yet, but we'll learn to very soon. We're going to evaluate these logs now. These logs equal something. There's some number that these logs are equal to. And these ones we can find because they're set up specifically to have kind of natural powers to them. Log base 3 of 9, this first one here, log base 3 of 9. Well, if you don't know what that is, and you don't really, I'd like to think about there being a variable there. Like, I don't know what log base 3 of 9 equals, so I'm going to call it x. Now if I do my circle thing, 3 to the x is 9, so x must be 2. That means that log base 3 of 9 is 2. I'm having very good handwriting today, and that makes me happy. So this is asking the question, 2 to what power is 16? When you see log base 2 of 16, it's really asking 2 to what power is 16? Well, 2 to the 4th power is 16. 2 times 4, 2 to the 4th is 16, so log base 2 of 16 equals 4. Pause it, take a second, and try to answer what log base 2 of 1/16 would be. And if you said -4, congratulations, 2 to the -4 is 1/16. Because remember, a negative power flips a fraction. So like a -3 would be 1 over 8. Because 2 to the 3rd is 8, and the negative flips the fraction over. Also try the next one on your own. Log base 1/4 of 64 is -3. 1/4 to the -3 is 64. That negative power, I know, causes problems. We'll talk a lot about it. We'll get used to it. For now, you just have to live with it for a bit. If you ever see an equation written that doesn't have a number down here, there's no base. We know it's base 10. We call that the common log, because all of the operations we do tend to be in base 10. So log base 10 of 10,000 is 4, because 10 to the 4th is 10,000. So log base 10 of 1/10,000th, -4. Sweet, moving on. We're going to graph log base 2 of x. I'm going to show a couple ways to do this, but what I want to do is think about numbers for x that are powers of 2. I want to plug powers of 2 into all these x slots over here. So what are powers of 2? Well, there's 2 to the 0, which is 1. There's 2 to the 1st, which is 2. There's 2 to the 2nd, which is 4. 2 to the 3rd is 8. But don't forget the other direction. And 2 to the -3rd would be an 8th. So I'm going to plug in numbers like an 8th, a 4th, a half, 1, 2, 4, 8. These are numbers that I'm plugging in to this x value here. Okay, let's start with 1. I'm plugging a 1 in for x. So I'm doing log base 2 of 1. Well, log base 2 of 1, 2 to what power is 1? 2 to the 0 power is 1. So that's really going to be a y value of 0. It's a 0.10. Log base 2 of 2. 2 to what power is 2? Now my circles are getting kind of small, so I'm going to stop. It's going to be a 1. Plug in a 4 right at that spot. 2 to what power is 4? And that's 2. Plug an 8 in up here. 2 to what power is 8? And that's 3. And then 2 to what power is a half? -1. 2 to what power is a quarter? -2. 2 to what power is an eighth? -3. I have these points: 1, 0, 2, 1, 4, 2, 8, 3, and then a half, -1, a quarter, -2, and a -4, etc., etc. This graph has a vertical asymptote. Why, pen? Come on, work with me. This graph has a vertical asymptote. Looks like that. It's an asymptote x equals 0. Usually now it asks us any questions, but you can't ask them really. So I will say this. This power on the 2's turned into these y values. And what it was equal to turned into these x values. Now it's getting really messy, so I'm going to undo all that. But just be aware that's what happened. At the same time, on this same graph, I'm going to graph y equals 2 to the x. I'm going to erase all this now. Y equals 2 to the x, just so you can kind of see how these compare to each other. So in purple was the log, in green will be the exponent, the exponential. I plug in numbers from -3 to 3. I get out an eighth, a quarter, a half, 1, 2, 4, 8. Graph those points. We've done this before. I have this, I have this, I have this, I have this, and that, and that, and that, and that. And this graph goes like this. So do you remember when I said that logs are inverses of exponentials? Well, there you go. It's a reflection over the line y equals x. And you'll note all of these points just switched x and y values. The x and y's just switched because logs and inverses. Logs are inverses of exponentials, and an inverse just switches x and y. That means you could graph another way if you wanted to. And this way is going to be, we're going to skip this for now. This way is an easier way to graph it first, but it'll eventually kind of get complicated. So I'll show it to you now and you can see if you like it or not. I can take this and convert it. I can do 2 to the y equals x with my circle thing. 2 to the y equals x, and that's what this is. So now I could really be plugging numbers in for y instead of for x. I could plug in -3, -2, -1, 0, 1, 2, 3 for y, and then 2 to the -3 is an eighth, a quarter, a half, 1, 2, 4, 8. That's going to give me the same curve that I had before. That's not a great graph, but we're going to live with it for now. So I'll show ways to do this again on Monday. And if you're not here Monday, I'll have a video for that as well. Let's keep going. I'm going to graph this now. Before I graph it, I'm actually going to make the points. That's what I'm really worried about, is how to make points. How to pick x values. I want to find the powers of 3. I'm going to bring 3 to different powers. I'm picking 3 because that's my base. So I'm going to do 3 to the -2, 3 to the -1, 3 to the 0, 3 to the first, 3 to the second. I'm not going to do 3 to the third. That's going to be too big. 27 is too big. If I pick these numbers, I get a ninth, a third, 1, 3, 9. These are the numbers I should plug in for x. Those should be the numbers in my x column, because those are all the powers of 3. All the numbers that 3 can be brought to give you a ninth, a third, 1, 3, 9. And the nice thing is whatever those powers were, that's my y values. This right here is my big long column of y values. Why? Why does that work? Well, think about 9. If I do log base 3 of 9, that's really asking the question, 3 to what power is 9? 2. 3 to the second power is 9. We're not going to graph this very well. You can graph it well if you really want to. It's going to also graph like that, but it's going to be steeper. It's going to move faster because this is a 3 now instead of it being a 2. That changes things. One more. Take a second and think about what numbers we should plug in for x. Pause it and think about what types of numbers we should plug in for x. And the answer is powers of a third. Powers of a third. So for example, 1/3 to the 0 is a 1. So I'm going to plug a 1 in for x. 1/3 to the first is a third. 1/3 to the second is a ninth. 1 to the third is a 27th, but that's too big. 1/3 to the -1 is 3. 1/3 to the -2 is 9. 1/3 to the -3 is 27. That's also too big. I'm going to live with that. Now when I think about evaluating this function, about plugging these numbers in for x, I'll start with 1/9. I'll do log base 1/3 of 1/9. Well, that's 2. This comes out to 2. 1/3 squared is 1/9. That means that this equals 2 if I plug a ninth in for x. This whole thing becomes a 2, and then it gets multiplied by that 2. So that's actually 4. Think about 1/3. If I plug a 1/3 in for x right here, if that becomes a third, this whole box becomes a 1. Because 1/3 to the first power is a third, so do 1 times 2, and that's 2. 1/3, log base 1/3 of 1 is 0, times 2 is 0. Log base 1/3 of 3, I do log base 1/3 of 3, well that's -1. 1/3 to the -1 is 3. So it becomes -1 inside this box, times 2 is -2, -4. So I have the point a ninth, 4, no, yes, a third, 2, 1, 0, 3, -2, did this in a funny order, I apologize, and 9, -4. My curve's gonna go. And that's my graph. Domain, we haven't covered that yet, I guess. X greater than 0, range, all real numbers. Sweet. If you have any questions, bring them to me. Just so you know, that's my new desktop picture of Wyatt, which is pretty adorable. He's eating sand. Hope you have a wonderful life.